Okay, I think we'll get started. So today we're going to talk about what are called auxiliary functions, enthalpy, and Helmholtz free energy and Gibbs free energy. They are not fundamental functions like entropy and internal energy that correspond to some directly physical thing, but instead they're just functions of convenience. We all as scientists agree on these functions, and it becomes very helpful to have them in thermodynamics. All right, so let's start with the first law. And we know that in its differential form, so infinitesimal change, we get heat and work combined to give the change in the total internal energy. And the second law gets entropy involved here with heat. And then finally, what is work? Well, we can express work as generalized force, generalized displacement. And in principle, all work is interconvertible, so we can lump all work into pressure volume work. Now, let's then go reversible. We've talked about this a little bit. So this is the conditions under which we're just getting whatever we're doing to happen. So in this case, raising the piston just a little bit, or compressing the piston just a little bit. Any pressure in the opposite direction will reverse the path. And under those conditions, the external pressure is equal to the internal pressure. And we talked about, when we were talking about the second law, that the conditions of the equality here are when we are in reversible conditions. That's essentially, I guess we should call this here Q reversible. That's the thermodynamic definition of entropy. So that means we can make these substitutions in and get this expression for the first law. And this expression is nice because, well, at first glance, it seems like it's not as general as this. This is always true. This is the first law, always true. This seems like we've done some things, especially we've said reversible conditions. But this is in fact general, because now everything involved is a state function. And so we found one way to get to this equation, but that is independent of path. All of those are independent of path. So the equation then is completely general. Now, as we look at this equation, we say, what is responsible for the change in U here in this casting of this equation? And that leads us to what are called the natural variables for this thermodynamic property. So for total internal energy, we can see that the natural variables are the S and the V. It's because the ds and the dv are causing this dt. Now, we can always do mathematical manipulations and switch these things out, but in all cases, the formula get more complicated. So the formula that is most simple is the one in which the ds and the dv are responsible for the du change. And so the independent variables are s and v. Those are the natural variables. Now, it turns out that it is very convenient to have different pairs of natural variables and not only be stuck working with S and V as the natural variables. And that's the impetus for bringing in these auxiliary functions. So we have three of them as we look at the other possible pairs. So let's switch out the V with the P. So we have S and P. Let's switch out the T and the S. Then we have T and V, and let's switch out both. So we have T and P. And those give us enthalpy, Helmholtz free energy, and Gibbs free energy, respectively. All right. So if you haven't had any calculus, you can just kind of follow along and wait till we pop out the other side over here on this side of the board. I'm going to show you, though, for those of you who might be interested in this, is how do we get these, the actually show that these are the right natural variables. And this is a process called Legendre transformations. So let's first do it with the enthalpy. So what we do is we say, okay, I want to change out, I have this, I want to change out this set here. This is what I'm going to focus on. And so we define H, and I'll use this three equal sign here to represent define H to be U, and then we want to cancel this, so we're going to go plus, because that's a minus, we're going to go plus PV. Okay, and right now it doesn't seem like we've gotten too far, but let's go ahead and look at a small change in H, little infinitesimal change dH, that's du, and then for those of you who've had calculus, this little differential operator is like a derivative, so it follows the product rule. So we have first times differential of the second plus second times the differential of the first. And now our du, well, what's that? That's over here. So dH is TdS minus PDV plus PDV. And there we get that cancellation plus VdP, and we have swapped out the V for the P, and that gives us the analogous formula. And indeed, if we check, yep, it's S and it's P as the natural variables here. So that's this formula here. Let me just do one more. I won't do all of these. Let's just do now Helmholtz. And then once you do enthalpy and Helmholtz free energy, Gibbs free energy is just doing both of those. So what do we want to do here? Well, let's think about that. I want to switch out the T and the S, and I want to leave the V alone. So that means I'm going to have an S and a T, so I'm going to take U, and now I'm going to subtract because this is positive here, and I want it to cancel TS. So then again, we look at what's going to cause a little change. Well, it's going to be du minus TdS minus SdT. Again, because of the product rule for this differential. So then dA is TdS minus PDV, that's coming from the du, and then minus TdS minus SdT. And so then our TdS's cancel, and indeed, our natural variables now, I'll write it this way, are T and V, just like we wanted over here. So A is a function of T and V as natural variables. And then G, right, just, you can try this on your own, is going to be U minus PV, or U plus PV minus TS. And so that gives us then these auxiliary formula. Okay, well, I've said now that these are auxiliary functions. They're not fundamental functions like energy or entropy, but we can still interpret them. Now, enthalpy is a little embarrassing because we use it all the time in general chemistry. And in fact, when you look at your book, you're not going to see DUs, but you're going to see DHs all over the place. We talk about enthalpy, and it really is kind of hard to get a beat on what it is physically, and that's because these are just convenient functions of convenience. But let's just look at the definition and see what that says. So, and then see what it did here. When we did this Legendre transformation, it canceled that VdP. So what it effectively is the energy sort of accounting for pressure volume work. And so under certain conditions, this should be a dq, under constant pressure and reversible conditions. Let's check that. So constant pressure, that's going to go to 0. Reversible conditions, by the thermodynamic definition of entropy, then dH is dq reversible. And so often as students go through general chemistry, enthalpy and heat are used synonymously. And they are kind of, even in higher level chemistry, with the understanding that we should know that enthalpy is not heat. Enthalpy is this auxiliary function. It's a state function. Heat is not a state function. But enthalpy is reversible heat at constant pressure. Reversible heat at constant pressure. So if we're running a reaction in a beaker and we're under constant pressure in the laboratory, the heat that's given off is indeed the enthalpy. Now you might say, well, how do we know that's a reversible path? And it does seem like, even if you have this has always been something that's a little bit been hard for me to understand. Even if you have an explosive reaction, you can still safely consider it as reversible. And I think how you want to think about that is down at the molecular level, the reaction is going backwards and forwards all the time. It's a very dynamic equilibrium. And so we consider that to be enough to be reversible. And so enthalpy and heat, you know now, based on what we've talked about, they are not the same things. But as you read your book, your Gen Chem book, you might be convinced otherwise because they'll be used synonymously. All right, Helmholtz free energy, that won't even be in your book, and it won't be in your physics book either. But it is important. We will use it a lot when we get to some of our higher level courses in this curriculum. We won't use it as much the remainder of the way out. But what it's nice about it is that if we look at this under certain conditions, let's go isothermal. So isothermal means constant temperature. And let's go reversible, in which case this is just work. And if it's reversible work, it's the maximum work. And so Helmholtz free energy is the maximum work. And that's where the name free energy comes from. You could think of it as it's the total amount of energy. It's the energy that's available to do work. And let's see why that's the case. It's the total amount of energy minus this TS term. Well, this TS term has units of energy, and you could think of it as, I like to call it entropic energy. It's the energy needed to keep the system disordered at temperature T. And so that energy is not useful. It can't be liberated from the system. It's required for the system to stay, to maintain its entropy. So what's left over is this energy available to do work, or free energy. That's a good way to understand Helmholtz free energy. Now, Gibbs free energy, very similar, but Gibbs, now, if we look at this, let's look at this bit here. That's just H, right? Oh, no, sorry. This is just H right here, these two. So this is like H minus TS. And we already said that enthalpy is a little bit tricky to define, but we can think of it as the total energy accounting for any pressure volume work. And so what that boils down to is that the Gibbs free energy is the energy available to do non-pressure volume work. And this is nice in a couple of ways. In a theoretical setting, we can get all the work over to pressure volume work, and then our non-pressure volume work will be zero. It's always good to make things zero, and we'll see that trying to make Gibbs dg zero is an important thing we try to do in chemistry. But then when we get to an applied case, like a battery or the capacitors, we've used some of those examples, then that's involving some non-pressure volume work. And oftentimes we are not interested in the PV works. So if the battery expands a little bit, or if we've got an ion channel going through a cell and the cell expands a little bit, that's not the essential chemistry that's going on, the chemistry that we're interested in. And so this captures nicely just the work that we're interested in. Then I want to get back to this expression here, H minus Ts. If we now take a differential of this, make the tiny change in G, well, that's going to be a change in H, and then again, product rule here. Now, let's go isothermal. That's going to take this term to 0, and we get this expression. And now let's just work that up for a macroscopic change, a big change, and we get delta G equals delta H minus T delta S. And this is the second most important equation in this section of the material and in this section of your general chemistry book. It relates the enthalpy, right, which is a type of energy, to the entropy. And we've said when we're talking about the second law and summarizing the laws that nature has these two big driving forces: try to minimize energy and maximize entropy. And it is this function here that captures that compromise. And what we will see, and we won't talk about it quite yet, but for a spontaneous process, delta G has to be negative. And so it gives us a clear criteria about whether something's going to happen or not happen. So if delta G is negative, then it'll just happen naturally. If delta G is positive, then it will require something from us to make it happen. And when it comes to chemistry, we like to categorize chemical reactions as favorable, they will go, or unfavorable, they'll go in reverse, or we would have to supply some kind of energy to get them to go. And so the delta G, this delta G equation, we're going to have several, but this equation involving delta G is critical. All right, so we aren't still getting to the point where we can do a ton of homework yet. Some of this isn't in your book. But again, tell yourself the story of this. We will get to the point where we are doing some homework problems involving equations like that. But we're in a period now where just try to keep getting these ideas down and thinking about how the big picture is coming together.